Okay, I think we're live, aren't we?
I do believe that we are live. Here we are. We're finally going to get into predicate logic. I'm very, very excited. We have Alex here. And Alex, I'm going to let you take it away while I try to deal with the housekeeping stuff in the back. So,
Okay,
hi.
cool. All right, so yeah, welcome back. So it's been a little while since the last time, and well, we last time I think I overreached a little bit and started to give a third lecture in the session, and I hadn't really looked through it and checked it, so we had to cut it short because I didn't have enough time, and we got to a point where I realised that one of the bits of the slides was actually wrong, so I was confusing myself. So the plan was initially to start off with that this week, but we're changing the plan again. I'll come back to that another day. So that was the material implication stuff. I think we'll probably snip it off the end of last week's video, ultimately, so it can have its own video on its own. So now what we're going to do is we've done propositional logic. Yeah, so we've said all that we need to about that, and now we're going to add to it by introducing some new terms which will allow us greater expressibility, so that we'll be able to analyze arguments that that are different to the ones that we've already been able to analyze. So propositional logic is very, very useful, but it has its limitations, as we'll see. Yeah, and so while we're moving on from propositional logic, we're actually building upon it. So we're not throwing it away, we're still going to be using it. We're adding some houses to the street that we've already built, rather than making a new street. Okay, so this is just kind of a recap, right? So yeah, in logic we study arguments and we're interested in their validity, meaning that a valid argument is one where if the premises are true, the conclusion is true. So what we've done so far is take English language arguments and turn them into their propositional argument form. So we've been getting, I've been giving you examples, and then what we would do is pull out of those examples the kind of core declarative fact bits and assign propositional letters to those, and then we would show the way that those facts were related to each other using the propositional connectives. So it was turning English sentences, if you like, into their propositional form, and then we use truth tables and trees, both equally good, although trees more amenable to complicated formulas. We use both of those as a way of testing, as a method of proof, to determine whether or not the argument form was valid. And then what we did was we kind of worked back into and then said, well, if the sort of symbolic form of the argument is valid, then we can conclude that the actual English language argument that we started was valid. So we've gone from an English language argument, broken it up, turned it into a formal logic, tested it, and then we come back and conclude something about the English language argument. So sometimes, but yeah, so we can test to see if something's valid. If we did that test and then we found that the formal bit of the argument was invalid, that doesn't mean that we can conclude that the English language argument is invalid, unfortunately. So I'll give you some examples and then I'll explain why that is. So we can certainly tell whether or not the formulas, like the formal bit, whether that argument is valid or invalid. It's just that the question is whether or not the translation from English into propositional logic was adequate. And if it's inadequate, then the test that failed and showed that it was invalid won't mean that the English argument is invalid. You can still have English arguments, like in English language, which are valid, but not translatable properly into propositional logic. So here's some examples. So there is a cake. Every cake is a pudding. Therefore, there is a pudding. Or another one. Everyone who is in Amsterdam is in the Netherlands. Kit is not in the Netherlands. Therefore, Kit is not in Amsterdam. It is raining. Therefore, it's possible that it is raining. If it is raining, then it will be the case that it was raining. So with each of these arguments, we wouldn't be able to, well, if we formed them in propositional logic, we would come out with the conclusion that they were invalid. And in each case, each of these arguments are actually valid. Here's a case in hand, right? So there is a cake, every cake is a pudding, therefore there is a pudding. Well, I've color-coded it already into their propositional parts, and all there is to all the structure that we can identify as propositions is just P, there is a cake, Q, every cake is a pudding, and R, there is a pudding. So the argument, when rendered into propositional logic, just becomes P, Q, therefore R. Now that's not a valid argument, because it could be that P and Q are true and R is false. As far as the propositional logic is concerned, it doesn't guarantee you that R is true just because P and Q are true. However, in English, those English sentences, they do guarantee that the conclusion is true if the premises are true. So propositional rendering of this argument doesn't track validity properly. The second one works the same way. Sorry, I'm getting some horrible echo there. Who's okay? Great. So yeah, this exactly the same way. So like everyone who's in Amsterdam is in the Netherlands. Kit is not in the Netherlands, therefore Kit is not in Amsterdam. If we render that into propositional logic, we get P not Q, therefore not R. Again, that's not a valid argument, even though in English, stated as it is at the top, it is a valid argument. So the translation fails. Again, it's raining, therefore it's possible that it's raining. It becomes P, therefore Q. Again, invalid. It's the case that it's raining, therefore it will be the case that it was raining, just becomes P, therefore Q. So again, an invalid argument. So the arguments are valid, but their propositional form isn't. So the reason that they're valid is that they're valid in virtue of a different structure, deeper structure, not just the propositional rendering is in a sense a kind of shallow way of representing the logical form. In many cases, it's adequate, but in those cases, it's not, right? So what is it that makes those arguments valid? Well, it's not that they're valid in virtue of simply arrangement of the propositions and the connectives that we've seen so far, these and, or, not, if, then, and if and only if. Right? That's not what makes them valid. So here are our arguments again. So the top one, there is a cake, every cake is a pudding, therefore there is a pudding. That's valid not in virtue of the propositions and the connectives, but in virtue of the meaning of there is and every. Right? It's those terms that we would need to introduce as logical operators, in a sense, to be able to cash out why that's a valid argument. Again, the second one, it's valid in virtue of the meaning of every, not, and the fact that Kit is a name. So we would need to be able to have names in our vocabulary as well in order to express why the second argument was valid. The third one, really, it's the behavior of the word possible or possibly that guarantees that if it's raining, then it's possible that it's raining. If we had possibility as a separate operator in our logic, then we would be able to express why that was valid. And lastly, this is kind of involved with tenses. So the reason that argument is valid is because the tenses will and was. If it's true now, then it will be that it was true. That's essentially why that last argument is valid.
Are we saying that they're valid just by our intuition, or are you going to go backwards and explain later?
Well, we do have an intuitive grasp of, to some extent, and differing from individual to individual, but we do have an intuitive sense of what makes arguments valid with greater degree of sophistication than just simply propositional logic. In the same way that somebody may, without being taught arithmetic or mathematics in general, they might understand intuitively something to do with how if you're increasing the sides of the field or something, then by a meter in each direction, that doesn't just mean there's one extra meter of area in there, something like that. But if they tried to explain it in detail, they wouldn't be able to give you the idea of a squared number or something. So we all here in this hangout, no doubt everyone here would have some idea, they would all hear all of these arguments as valid, and they'd probably be able to give you some kind of explanation for why that's the case. But my point is that if you tried to say that it was valid because of the resources of propositional logic, then you'd find that you run out of expressive power. You wouldn't be able to pin down why these arguments are valid and why they're not. Strictly speaking, the first two would be valid in, we'll go on to be able to explain the first two in first order logic. The second one, you'd need to have a modal logic, and the last one you'd need to have a temporal logic. Although I think I'd say that here. Right, yeah, okay, so the predicate calculus is a logical language that can express form the first two arguments, the cake and kit. And then modal logic and temporal logic would be for the final two. Yeah, so my particular bit of philosophy that I've published papers in is the type of logic that has both modal operators and temporal operators in it. So it's called temporal modal logic, but you can just think of either of those two as two separate ways of upgrading the logic to have more expressive power. Anyway, so we're not going to look at the temporal logic or modal logic in this course, although I'm kind of tempted to keep going with this and maybe do that at a later date, but we'll maybe discuss that another time. Yeah, what we're going to do from now on is look at predicate logic. It's sometimes called predicate logic, first order logic, the predicate calculus. All of these terms mean the same thing. What we're doing is upgrading propositional logic, basically, so that it can talk about names, so we can name individual things or people, and we can talk about expressions like every person is such and such, or everything is this and that or the other. So we can, instead of just talking about facts, we can, like, I'll explain it more as I go on. There's no point me just trying to explain it. The whole point of this lecture is explaining what we're doing here. So look, what we're going to be introducing as our new bits of vocabulary are constants, predicates, and relations. At least this is what I'll introduce you to in this first lecture. Hopefully we'll cover a second lecture in this session as well. But to begin with, I just want you to focus on these things, right? So we're going to be adding to the propositional logic three new types of vocabulary, essentially. Constants, which you can think of constants as being names, like proper names, like Helena or Alex or whatever. What they do is attach to a thing in such a way that the way that it picks out that thing doesn't vary, right? It's constant. I guess it's exactly the same distinction as a constant and variables in algebra, if anyone finds that easy to think of. So you might number, or you might attach a label A to a number or something, and in a sense you're naming that. So sometimes you can express algebraic relations between numbers without actually having to talk about the numbers themselves. You just need to keep fixed that, you know, A, B, and C pick out numbers. And then sometimes you'll have like a placeholder that you could put any constant into, which would be a variable. And that basically will be the same way this works. So sometimes we'll have variables as well as constants. This will become clearer as we go along. Anyway, that's what one will be. It's essentially talking about names either in a specific or general way. The second part is we're going to be introducing predicates and relations. I'll talk more about them in a bit. And lastly, we'll be introducing quantifiers, which I'll explain more about them. I'm not going to bother trying to explain them right now. Okay, so constants, predicates and relations today, or in the first half, and quantifiers in the second half. Okay, so constant is a name like Kit. I've explained that already. So a predicate is an expression of a property. That will do as a kind of philosophical gloss for what we're talking about here. So it's a property like is clever. So you could say Kit is clever, and then that would be the conjunction of a constant and a predicate. Now, a relation is really the same thing as a predicate. It's just that it's more complex. So a relation is a predicate, but it connects more than one thing. So it might be that Kit is taller than Alex or something, right? So it would be, it's basically mathematically it's the same thing as a predicate. It's just a two-place predicate, or a predicate is a one-place relation. But we've got, I think we've got these terms in English anyway, predicate and relation, picking out these that one of them just expresses essentially a one-place property, and relation picking out a two or greater place property. This will become clearer as we go along. So here's an example. Kit is in Amsterdam. So Kit is the constant, and is in Amsterdam is the predicate. So yeah, as I said, so constants pick out individuals, predicates express properties. Is kind of just think about it as the predicate being is in Amsterdam, or you could think about it as a kind of invisible glue that just sticks together constants with predicates in Amsterdam, sort of blank in Amsterdam or something. And the is just to say like these two things go together. It doesn't matter so much. The logical form will be clearer as we get into it. The actual like tying together, tethering English language grammar and vocabulary exactly to a logical form is starts to become quite complicated and needlessly difficult. Don't worry too much about it. It will become clearer as we do it, example by example. Here's some examples anyway. Gordon is Scottish. Barack Obama is Democrat. Is a Democrat, I suppose I should say. Anyway, whatever. Childish is what Jason is. I wrote this in 2011, in case anyone's wondering. Okay, so in the first example, Gordon is constant and is Scottish is the predicate. Barack Obama is the constant, second example, and is Democrat is the predicate. So in the bottom example is just to show you that sometimes it can be the other way around. Obviously, childish is a predicate and Jason is constant in that example. So this is what I'm saying. Sometimes, then we've got this is what Jason is. There's lots of other kind of flotsam and jetsam in the English sentence, but really there's the same logical form as the first two. It's it's just saying that there's this predicate that applies to a particular thing. Okay, so let's start to see how we would translate sentences of this form into the predicate calculus. So Kit is in Amsterdam, constant predicate. So here's our dictionary, right? We'll for constants, we're going to be translating them as lowercase letters near the beginning of the alphabet, just for some kind of procedure so that we don't get confused by it. And then predicates, we're going to be taking uppercase letters like this capital P, and here X isn't a constant, it's a variable. So variables will always be at the end of the alphabet. So it's really just a placeholder here that needs, as an empty space that needs to be filled by a constant of some description. So PX just says like ... is in Amsterdam, right? Or X is in Amsterdam, it's an empty space. If we fill it, the logical form would be like this. So it's like saying P of A. So it says that like Kit is in Amsterdam once we've translated it. So the propositional form of Kit is in Amsterdam is PA, like written like this, predicate P and constant A. If we do exactly the same thing here with the other example, even though the predicate and constant come in a different order in English sentence here, it doesn't make any difference. The logical form, we write it out in exactly the same way. Right? There's a thing, a constant, picking out Jason, and predicate is childish. And if we call that P and Jason is A, then it's exactly the same logical form. We could go wrong with this, right? It seems like this has a similar logical form. Buses are red. And we could go, okay, then in that case, buses is constant A, and red is some predicate R, and then we translate buses are red as R of A. But buses isn't an individual. Buses is a group, right? It's not. You don't express buses with a constant. Constants are for individual things. We don't need to have like a metaphysics of individual things here. It doesn't really matter what that means, but the point is it's obviously not a group. It's not the same thing as a collection of things. So if this was on the test or whatever and it asked you to translate buses as red, you wouldn't translate it like this. I haven't told you how you translate that. We'd need to use quantifiers, but just be aware constants are just names, essentially like proper names. Okay, good. Now let's look at right. So here's a way. This is nice. So we can show you how predicate logic is not a different logic from propositional logic. It's just an extension of propositional logic. So we can still use the resources of propositional logic and the resources of predicate logic together. So we've got here, Obama is a Democrat and Cheney is a Republican, right? So we can pick out our constants, Obama and Cheney, and we can pick out our predicates, is a Democrat, is a Republican. And then we've got the word and in the middle, which we already know from propositional logic is one of our propositional connectives. So we can write this whole sentence up here as the following logical form, right? PA, so A being Obama and P of X being is a Democrat. So we can say, that means Obama is a Democrat. And QB, so Q being is a Republican and B being Cheney, QB says that Cheney is a Republican. And we're saying both of these two. So it's Obama is president and Cheney is a Republican. So it's where we had before in propositional logic just P's and Q's standing for facts. In a sense, now we've got certain facts we can reveal a more finely grained logical form, like P of A. And so it's P of A, this thing is true, and this thing is true. So it's exactly the same. It's a propositional form, but with a deeper level of structure, if that makes any sense. Okay, let me just have a drink. Any questions at this point? Are we all good?
So far, so good for me. Anybody have any questions? Okay, let's go on.
Okay, good. Either everyone's muted or there's no questions. Either way, let's carry on. Right, so let's look at relations now. So very, very straightforward, really. If that's all cool so far, then relations isn't a problem, right? So if we've got these types of expressions, so Bill voted for Hillary, Cheney is a seventh cousin to Obama, Obama is younger than Bush, these types of sentences. So the distinguishing feature here is that we've got two constants, Bill and Hillary, and a relation between those two. So it's Bill voted for Hillary. Same here, two constants, Cheney, Obama, and the relation is the seventh cousin to, and here two constants and the relation is younger than, joining them together. So the way that we would write these out is we'd have a dictionary, A for Bill, B for Hillary, and then we've got this, it's a predicate basically, but with two argument places. The argument places means slots, empty slots that we can put constants into. So it's we would express Bill voted for Hillary, provided that was the dictionary, by saying R of AB, right? So A is related to R by the voted for relation. So A voted for B. That's what that says. Be aware, of course, that A voted for B isn't the same as B voted for A. Obviously, like in English, the order of the constants around this relation matters. It's not symmetric. So if Bill voted for Hillary, it doesn't mean that Hillary voted for Bill, right? They express two different things. So what's the ordering of the constants in this proposition, this formula here, the ordering, the fact that A has to come before B in order to express the fact that Bill voted for Hillary, follows on just like it does in English down into the logical form we're putting in its predicate logic. So we can express either quite easily. So I mean, that says that Bill voted for Hillary, and that says that Hillary voted for Bill. So in a sense, it's quite easy to express those two different facts. We just need to switch around the order of the constants. I mean, some relations are symmetric, so it doesn't matter, and some of them are not. So if you're thinking about an asymmetric relation, then that matters. Okay, here's another asymmetric relation. So it's two constants in a relation. Exactly the same thing again. Really, it's, put the dictionary, A for Obama, B for Bush. R means is younger than, and so the logical form would just be R of AB. And yeah, so here's, I suppose I haven't really been pointing this out, but this is the thing, this R of AB is something that we would consider to be a proposition. So it's true or false. A proposition basically just means, like a working definition of proposition is just something that you can attach a truth value to. So when I'll go into this in a lot more detail, but we'll see later on that these operate syntactically on the same level as propositions did. So they're the things we combined with connectives, and they're things we need to put brackets around. They're the things that get truth values. They're the things that we will be making our trees only have propositions, so things like this in when we're doing trees. So yeah, just what we're doing is giving a deeper kind of logical form of propositions, being something like this. Okay, good. Yeah, again, the order of the constants matters. Otherwise, you're going to be saying that Bush is younger than Obama. Good. So, okay, and then here's one with 3 constants in. Joe gave Dave's notes to Kate. So we've got A, B, and C being Joe, Dave, and Kate. And then we've got this 3-place relation, R of X, Y, and Z. X gave Y's lecture notes to Z. So the logical form of Joe gave Dave's notes to Kate is this. There's really no reason to limit how many argument places, how many X, Y's, and Z's we can have for a relation. It could be infinite. It doesn't really matter. So the only difference between a predicate and a relation is that a predicate only has 1 argument place, whereas a relation has as many as you like. But if we were being ultra mathematical about it, there really isn't a difference between predicates and relations. We could just call them all predicates, and you have 1-place predicates, or 2-place predicates, or 3-place predicates, or whatever. So yeah, the distinction between predicates and relations is just because we have that distinction in English or something. Like we're relating things means there's more than one thing, whereas predicating something of something doesn't have that connotation. Okay, so we've got now another example where we've got 3 constants and we've got some propositional connectives in there as well. So we've got Hillary, that's a constant, is younger than Bill, so this is a relation. Bill is another constant. Barack is another constant, and we've got Hillary occurring again here, and is younger than relation occurring twice. But we've also got the whole thing embedded in an if-then conditional. So how would we translate that? We'd say if this is our dictionary, that Barack is A, Hillary is B, and Bill is C, and RXY is the X is younger than Y relation, we'd say if Hillary is younger than Bill, then Barack is younger than Hillary. Right, so it's again, these things are propositions, and we've got our rules. We know that this is a binary connective that takes propositions on each side. And it's the if-then connective. So we're saying if R of BC, then R of AB, basically, and that's codifying this top sentence up here. Is that clear? Yeah. Okay. Let's assume.
Yes. Yes.
Deafening silence. Good.
Yes, it's clear. I think we're okay.
Okay. Good. So again, here's another thing that we could go wrong with. It's the same thing as before, really. But if you wanted to say trains are faster than buses, don't chuck in A for trains and B for buses, because A and B are constants, and they should be the sorts of things that you apply to individuals, not groups. Okay, good. So that's cool. Right, so let's just recap, right? In terms of vocabulary, we've got our familiar propositional logic vocabulary. So we've got propositional letters, P's, Q's, and R's. We've got connectives, the and, or, not, if, then, if, and only if. And we've got our disambiguating, what they call brackets. So all we're doing now is adding to that. a load of new stuff. So now we've also got constants, we've got predicates, and we've got relations. And we'll just conventionally write lowercase beginning of the alphabet. These stand for constants. Uppercase could come from any part of the alphabet, really. It'll be obvious. And relations, normally I'm going to use R for relation just because it begins with the letter R. Anyway, as I said, there isn't really much of a distinction between these two. So all we've done is we've added to propositional logic the fact that we've got things, names, and things we can say about those names, that they have individual predicates or that they're relating to them or more related to one another. And so it's not a new logic, although it's new bits of logic. We're just upgrading propositional logic into first order or predicate logic. So we've got a couple of new rules of grammar. So we already saw that the idea of a well-formed formula is that if any proposition letter on its own counts as a well-formed formula, if this is a well-formed formula of any type of complexity, then chucking a negation in front of it results it in a well-formed formula as well. So by well-formed formula, we mean something which is part of the language, something which could be evaluated and used. It's not nonsense, something which we can make sense out of. And if we've got two formulas which already count as being well-formed, then we can combine them by these binary connectives that we've seen in the last couple of weeks. And these are the grammatical rules of the propositional calculus. So every formula, no matter how complicated in the propositional calculus, is merely made in this way. Or you could, if you like, you could start with a complex formula and you could break it down into bits by so you could say, well, here's my complicated formula, A if and only if B, or something. You can break it down into its component parts. So that means that this is a well-formed formula, and it means that this is a well-formed formula. And if it turned out that A is in fact just a label that itself is a complex formula, you'd be able to break that down again. It's going to be either a negation of something, or it's going to be a proposition letter on its own, or it's going to be another binary connected. There isn't anything else going on. Like the whole of propositional logic in terms of grammar, it's very, very easy and straightforward, and not like learning a foreign language or something. This is the grammar. That's it. Once we've got that in our heads, as that's the grammar of propositional logic, then we're just adding to it a couple more rules. So we're just saying that if P is a predicate and A is a constant, then P of A is a well-formed formula. And if R is a relation of n places, that means that if it, R of xy would be a two-place relation, etc. But we're generalizing it. So if R is a relation of n places and A1 through to AN are constants, then R1 through to Rn is a well-formed formula. So however complex our relation is, if that's a relation and it's all got each of its places, its argument places are filled with constants, then the result is a well-formed formula. And that's it. So there's more to it, but so far this is what I've introduced to you. So two extra grammatical rules. We haven't quite got the whole of first order logic in place yet, but this is all we've added in terms of grammar to the propositional logic. Okay, good. So that's the end of lecture 1. So just as I pull up lecture 2, are there any questions or any comments or anything?
No, you're good so far.
Okay, good. So let me try and figure out how to change what I'm screen sharing. I always forget how to do this. Yes, good. There we go. Good. Oh, I need it on my screen. Okay, nice. I know that's one. Nice. Okay, good. So we're going to introduce slightly more the rest of the vocabulary from first order logic now. So we're going to be adding in quantifiers as well. So yesterday, or just a minute ago, as it might be, I've shown you how we can say things like this sentence: Michael is Dutch, or Johannes is Dutch, We can see our Michael, or Michael, sorry, is constant, and Dutch is a predicate, and Johannes is constant, and Dutch again is a predicate. So we can say it like this: it was like P of A or P of B. Like Michael being A and Johannes being B. One of them is Dutch. This is how that the logical form of that sentence gets cashed out in terms of first order logic. And here's a slightly more complicated one, but really it's not that much more complicated. We've just got Michael is married to Carrie and she is English. Well, we know that the word she isn't really a constant, but what it's doing is it's referring back to Carrie, so we can consider it a constant for the sake of cashing out what the argument, the logical form is. So it's just saying Michael is married to Carrie, that's R of AB, given this dictionary over here, and the second bit, and she is English, and that's referring to Carrie, so we're saying if P of X means is English, and we're saying P of B. Okay, great. So hopefully all of that's fairly straightforward. So let's look at a little bit more. This is just recapping what I said a moment ago. So as the two extra grammatical rules, I'm just going to skip over that. Right, so here we're going to start some new stuff. So here's 4 sentences we wouldn't be able to express given the resources I've given you already, but that we will be able to express by the end of this lecture. So there is an omnipotent being, everything is material, there is a possum in Australia, and every possum is a marsupial. We can't express those things yet, partly because they don't have constants in. So we're referring to things, but we're not referring to them by naming them. We're referring to them in more kind of oblique manner. So here, let's look at this sentence. There is an omnipotent being. So as I said, yeah, we were talking in terms of constants yesterday, so that talks about specific individuals. And this is just saying, in essence, it's saying there is at least one individual with a particular property. But we're not saying which one it is. We're just saying there is an omnipotent being. But I'm not saying, you know, this thing is an omnipotent being. So it's a slightly subtle distinction, but not too difficult to grasp. I think that there is an omnipotent being is a true sentence, even if you haven't said who it is. That is the omnipotent being. Or if I said there is a murderer, or the murderer got away with it, or something, I could say that without naming the person in particular who I think got away with it. I might not know who it is that got away with it, but because no one got done for the crime, I know it's true that somebody got away with it. So we want to be able to say that these things are true, but we don't want to have to use a constant to do so because we don't know who it is. So this is the point of using these quantifiers instead. Right? So we're going to be saying this backwards E, or as an old lecturer of mine used to say, it's not a backwards E, it's a rotated E. You'd think that the difference would be nothing, but apparently back in the day when they would print things with you know, like a stamp or whatever, in order to get an existential quantifier, obviously you can't invert a stamp, but you can rotate it. If you turn it, you know, rotate it through 180 degrees, it's now pointing backwards. So it's not a backwards E, it's a rotated E, whatever. Anyway, we're going to be using that as it's a bit like a predicate, but it's not to be confused with a predicate. It's a quantifier, which is kind of distinct. We just read it as saying something like there exists, or there is at least one such, or something along those lines. That there is something which is ... That's basically what it means. So this sentence says there is an omnipotent being. We translate it into its logical form like this, and that's supposed to mean there exists an X such that X is omnipotent. So there exists an X. This means the existential quantifier means there is an X such that, and then whatever it is that follows from the quantifier is what we're ranging over. So there's a formula that follows, and the formula's got to have a variable. It's got to be the same variable that we've got here after the existential quantifier. So there is an X such that P of X That's what this is saying. Something is x in the most simplest form. But yeah, it's important that two things. There has to be a variable. There has to be a space free in the formula that follows from the quantifier, and that has to be the same variable that's used in the instance of the quantifier that came beforehand. We need to know what x it is in this formula that we're making the existential claim about. So yeah, so saying there is an omnipotent being is just to write it like this: something is omnipotent. So there is a tennis player. It's just P of x means x plays tennis. It's just a predicate, and then we say there is something which plays tennis. That's how you say there is a tennis player. But you don't want to say like there is a red car. Why don't I like this? I can't remember why I put this in now. Damn it, I should really do more prep for these before I start talking. Okay, so I guess it's the reason that this is wrong is it's sloppy, really. That there is a red car. In a sense, it's a conjunction of two. Right, sorry, yeah, I should read ahead. Yeah, there's two predicates going on here. It is red and it is a car. And we're saying there is one thing which is both of those. So you don't translate it as P being is a red car. We can do better than that. And we can say there is one thing, which there is some X somewhere, and it's both P, i.e. red, a car, and Q, i.e. red. So we're saying there is a red car means there is something which is both a car and red. So we're using quantifiers, using predicates, and we're using the propositional connectives to spell out in as fine-grained detail as possible what the propositional, what the logical form of there is a red car is. I guess you wouldn't do that with tennis player. There is someone who plays. Being a player, I guess in American the player is a thing, but it's not like in the same way that being a car is separate, distinct predicate that's being conjoined with the predicate being red. Tennis player is one predicate, really. That's why I'm translating it here just as P of X, whereas red car is two separate predicates that are being conjoined. Okay, hopefully that's clear. Is that clear?
Yes.
Okay.
Yes, for me. Does anyone have any questions so far?
And there's no stupid questions. Feel free. I'm not going to be. I quite like questions, really.
I think we're okay.
All right, good. Let's do another one. There's a bald man wearing glasses. We translate that so P of X being X is a man, so we need to have this man part. We need to be able to say that something is bald. So we're going to have another predicate here. It's bald and is wearing glasses for the last bit. So really this is a conjunction of three predicates. There is a bald man wearing glasses. Means there is something, some X, such that X is bald, X is a man, X is bald, and X is wearing glasses. Now, I've put the where the punctuation goes, where the brackets go here, doesn't really matter. I've put it around here, but you could equally have put the you could have PX and QX and RX, and it won't make any difference because conjunction doesn't really care about that. For making it utterly unambiguous, I've done it this way around. Basically, if you've got a large string of conjunctions or a large string of disjunctions, it doesn't make any difference where you put the inside brackets. You could just have outside brackets, and it wouldn't really make any difference. Where you have to be careful is if you mix them together, then you do. It's a bit like the way that if you had mathematical operators like x plus y plus z plus whatever, it wouldn't matter whether you had x plus y in brackets and then plus z as the outer brackets, like x plus y plus z, or x plus y plus z, it wouldn't make any difference. But if one was a plus and one was a minus, then it would make a difference. You'd have to be able to distinguish those two properly in order to. Actually, even then, it wouldn't make a difference, would it? If it was plus and minus. Damn it.
Once you get multiplication in there, then
once you get multiplication in there, yeah, right. And that's when it stops being commutative, I believe, is the term for that. And anyway, I'm sidetracking. Let's just plow through. So there is a blonde woman and a brunette woman. We need to have the predicate is woman, is blonde, and is brunette. And then we say there is something such that it's a woman and it's blonde, and there is something such that it's a woman and it's brunette. Now, in a sense, you know from this that there is a blonde woman and a brunette woman, that we're talking about two different women, of course. And you might say, well, I'm using X for both of these, so have I inadvertently spoken about the same woman in this? Have I said that there's one woman in particular who's both brunette and blonde because I've used X's? And the answer to that is no, at least not necessarily. I haven't committed myself to that in this logical form. I've certainly left it open one way or the other whether these two things are the same. But basically this quantifier here, the existential quantifier, has a range, and it ranges merely over the formula that follows it. When the outermost set of brackets on the formula that follows it close, it stops being applicable to what comes next. So I'm saying there is something such that it's blonde and a woman, and then this says again there is something such that it's blonde, a woman and brunette. But don't think that just because I'm using X here and I'm using X here that means that they're the same thing. These are variables at the end of the day. They're just empty slots that are open. It might be that one thing fills both of these variables, but it doesn't have to be, and I haven't committed myself to that. And we know that in English, at least you can't be totally blonde and totally brunette. I guess you could have some blonde hair and some brunette hair, but you know really that this means that there's two separate women. I haven't really specifically said that here. Right at the end of this course, we will use predicate logic to be able to express numerical values. So you could say there's 3 women over there or something. Anyway, yeah, before I get sidetracked more talking about that, let's just crack on. So if you wanted to say there is a tall man outside Buckingham Palace, you'd say A is Buckingham Palace. So we're using a constant, a name. Obviously, Buckingham Palace isn't a person. That doesn't matter. It's still an individual thing that we can pick out. We want to say there is a tall man outside it. So we need a predicate for is a man and is tall, so that we can talk about that thing. So we need to be able to say there is something such that he's a man and he's tall, and it's related to A. This X is related to A. But so notice after the quantifier, there's one set of brackets that opens up this one, and it closes here. So all instances of X that follow this one, and this one, they're all being bound by this quantifier. So they're the same X. These X's are all the same thing. Let's just go back to the previous example so that it's crystal clear. In this one, these two instances of X are bound by this quantifier. So they're the same thing as each other. But these two instances of X are bound by this quantifier. So while these two are the same, refer to the same thing, there's no reason to suppose that this X and this X need to refer to the same thing. So the range of the quantifier is quite an important concept to get into your head. That's the range of this quantifier, and that's the range of this quantifier. And then over here, this is the range of this quantifier. So the brackets, if you're wondering what the range of the quantifier is, you just need to ask yourself where this next bracket after the quantifier, where does that shut? Well, it shuts here. So that shows you, delimits the range of the quantifier. It's a very useful, it's sometimes called the scope of the quantifier. It's very useful for being able to draw fine distinctions. Scope distinctions are some of my favorite things, a sort of favourite philosophical tool of many philosophers, to be able to draw out scope distinctions. So I really like this one where it's, so there's this, is it too early to do it? So I think it's fair enough. There's a joke by Bertrand Russell, which I think is probably the best philosophy joke, and it's to do with the scope of the quantifiers. Now, almost always, whenever I've told this joke in lectures, nobody laughs, but I don't think that that is testament to it not being funny. I just think that that is because maybe it's the way I say it, or maybe it's that people, I say that it's the best joke in philosophy, and then it's not that funny. But it is, anyway, the best joke in philosophy, regardless. And it's something like, so there's this rich yacht owner who's boasting to his friend about the size of his yacht. And then when he takes his friend down to the harbour side, his friend says to him, "Oh, I thought your yacht was larger than it is." And then the yacht owner angrily retorts back to him, "No, it's not larger than it is." Like, that's the joke. I think that's really funny because it's a scope distinction between, like, well, basically the phrase, "I thought your yacht was larger than it is." If you put it like that, he didn't think that the size of the yacht is bigger than the size of the yacht, which is what it sounds like it's saying if you take it literally. Rather, the size of the yacht was bigger than the size he thought that it was. And so the difference between the way that the guy says it, which annoys the rich yacht owner, because it seems like he's expressing some, how could the yacht be bigger than the yacht actually is? It's the scope distinction between what the range of what he's saying, "I thought that," ranges over. Does it range over the size of the yacht and the size of the yacht, or is it that the size of the yacht that he thinks is smaller than the size that the yacht actually is? So in order to understand that joke, you have to have quite a good grasp of scope distinctions. Maybe that's why it doesn't go down too well when I say that in logic lectures. I'm assuming that because no one unmuted themselves and cracked up laughing, but it's gone down about as well as normal, so I'll crack on. Okay, so blah, blah, blah. There's a woman who loves John. It's just applying a predicate for is a woman and a two-place relation for X loves Y. We've got a constant in there, but we need to talk about there is a woman. So we're saying there is an X. Now this open bracket shows you the scope of that quantification. There is an X such that X is a woman and X loves John. Great. It's easy, I think it's easy enough when I'm explaining it out like this to see, okay, that's how that works, give me the dictionary, that makes sense, I can get it. Kind of harder if you just sat down on your own and went through some examples to try and write out the logical form. It's easy to get it wrong, especially when you first do it, and to put things in the wrong order, or to end up saying a formula that doesn't really mean anything if you analyze it properly. But I think the more examples you see of it, the more it makes sense. And first order logic, this type of being able to translate a sentence like this that mixes propositional connectives, constants, relations, predicates, and quantifiers, if you can do that, you can more or less have the range of vocabulary that analytic philosophers have. So they might express an argument about ethics, or I don't know, an argument from politics or whatever, any area, metaphysics, whatever, anything. And you quite often find if you pick up a professional philosophy journal in analytic philosophy, that at some point in it, that someone will be saying something and cash it out in logical symbols, but they won't really, most of the time, depends what you're reading of course, but most of the time they don't really go much further than having this kind of level of complexity to it. So it might look daunting when you open it up and you see, not only are there loads of technical words and jargon and stuff, but also there's these like incomprehensible symbols and stuff going on. But really, yeah, a lot of the time, maybe 50% of the time, you can get away with not knowing any more than just first order logic, predicate logic, what we're doing now, and you'll be able to get most of what you're reading. And even then, when the extra stuff, most of the time, I don't know, out of the remaining 50%, probably more than half of that, you're only going to be building on what we've got already. So it won't be a different logic. It will just be adding yet more houses to the street that we've already built. So this gives you like a really good grasp of logic as it's used by philosophers anyway, which is why it's a compulsory course when you start at a good analytic institution. You will have to do logic first, and it'll be compulsory. If you fail it, you can't progress to year 2. You have to pass it. There's not many courses that are like that, but logic is so fundamental and it's used by everybody that you have to get to grips with it. So, and I think it's also useful if you're, I don't know, if you're, I think everyone should have at least a propositional logic in their heads and a basic understanding of predicate logic, like everybody. And it sounds stupid, but it's very, very useful for clearing up how to think. Yeah, basically, I think everyone should be able to see what's going on in Russell's yacht joke. If the whole world was able to do that, I'd be happy for some reason. I don't know. I just think everybody should. It's like a basic understanding of chemistry or basic understanding of Newtonian physics. You don't have to do really complicated stuff, but you should have a basic idea of how these things fit together. And I think this type of logic, it's not that difficult. Everybody should have a basic idea of how it works. Anyway, get off my soapbox and carry on. Okay, so now we've got everything is material. So last time we treated sentences that said of a single individual that it has a particular property. Right, this sentence says of all individuals that they have a particular property. Everything is material, it says. So now we need another quantifier. There's only 2, so this is the last one. Whereas the existential quantifier said there is something such that, or there exists an X such that, blah, blah, blah. This says for all or every. So it's like a strong version of the existential quantifier in a way. It's an upside down A or a rotated A, depending on how you want to put it. Everything is such that, or for all X, M of X. Everything is material. Yeah, so it's where the existential quantifier picks out, it says at least one thing is, this says everything is. Okay, so if you wanted to say everything is an illusion, you'd say, have our dictionary where P is the predicate for is an illusion, and you'd say for all X, P of X. All possums are marsupials. You'd say PX is being a possum, QX is a marsupial, and you'd say for everything, if it's a possum, then it's a marsupial. So, yeah, so in order to capture this, all such and suches are such and such, we're using conditional. Everything is such that if it's a possum, then it's a marsupial. So it's a bit like having a set and a subset. So here's the set of things that are possums, and the set of marsupials is a subset of the set of possums. So while material implication looked weird in propositional logic, the way that it worked, I think that it makes a bit more sense when you come to start doing this type of logic, where we'll be looking later on at sets and subsets, and we'll be using a bit of set theory to show the models and how they're. So the semantics for propositional logic was just basically showing how the formulas basic formulas have a truth value, like the truth assignments, and then we can just like crunch it into a truth table, and that gives you all the truth assignments for all of the more complex formulas. So that, in a sense, that was the semantics. And there's really nothing to it apart from just saying true and false for basic parts, and then crunching through the combinations. With predicate logic, with this first order logic, the semantics is going to be much more complicated, and we're going to be, like I said, talking about set theory a little bit. It's not going to be anything that people won't be able to understand, but it is much more complicated than the ultra simple just T's and F's or whatever that we had with predicate logic. With propositional logic. But part of the benefit of doing this slightly more complicated semantics is that you'll be able to see that conditionalization, this material conditional, really just corresponds to being a subset. But anyway, I'm digressing a little bit, but wait and see. It'll be nice when we get there. Great. So we had buses are red before. We were translating it wrong with using a constant instead. So now we can actually translate it properly. So buses are red means, well, on one way of reading it anyway, everything is such that if it's a bus, then it's red. Don't want to get sidetracked again, but this phrase, the English phrase buses are red, because it doesn't actually have the phrase all or every in it, hovers on the boundary between being a full-on universal generalization, like all possums are mammals is a universal generalization that applies to everything. Buses are red, on the one hand, could be read as a universal generalization, and if so, this is the logical form for it. There is quite an interesting literature that's an overlap somehow between kind of philosophy of language and linguistics and psychology, where it's an area someone was talking to me about the other day, and so I started reading papers about it. But it's about generics. This counts as a generic. Buses are red. And other examples, you might say something like sharks are dangerous, or sometimes more controversially, some people will say generalizations like Muslims are terrorists or something. And so there's a lot of interest in how to understand these types of generics. Is it wrong to read this as, so if someone says sharks are dangerous, and then you read it as a universal generalization saying everything is such that if it's a shark then it's dangerous, or finding one thing that's a shark, this is true, it is a shark, but this is false, it's not dangerous, that would falsify this conditional, because the antecedent's true but the consequent is false. If you found a non-dangerous shark, does that disprove the generic that sharks are dangerous, or is it just, well, it's still true that sharks are dangerous, it's just, it means something like less specific than a universal generalization. So I think a lot of internet debates where people say things, there's all sorts of stupidness about battles between genders where one gender will say to another, all of you lot are like this, and then they'll say, oh no, I'm not like that, or something, as if that's a defeater to the claim, men are bigoted or something. Well, I'm not bigoted. Yeah, but it's still true that men are bigoted, blah, 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 round and round it goes. It's just a kind of, like, what we're doing here is like looking at the difference between a universal generalization, which can be falsified by finding a single counterexample, and a generic, which isn't necessarily supposed to be translated with this logical form. Maybe generics have some other logical form, or maybe they're quasi-logical, they can't really analyze them because they're not precise in their essence or something. Anyway, so I think that it's interesting just to note as a side that it's not always 100% clear whether you should translate a sentence like this into the logical form like this. And a lot of what goes on the internet and in other more interesting bits of philosophy that relates to real things like the way that we generalize about stigmatized groups in society, or things in general like sharks or whatever, a lot of that revolves around picking up distinctions between this type of sentence and this. Anyway, the point is, if we generalize it, like if we formalize it in this way, buses are red, not as a generic but as a universal generalization, then we can express it in predicate logic. And we do so by using the universal quantifier, just to track all the way back from a massive circle tangent back to what we're actually talking about. And if anyone's getting annoyed, I guess really technically speaking there should be brackets here and here in order to mark out the range of this quantifier, right? It ranges over what follows it. But I drop the parentheses when it's obvious. So hopefully, if Rumpus was here, he'd be complaining that there wasn't brackets on either side of this thing, but you know, he's not.
Say, whatever you do, don't put brackets on either side because they're irrelevant.
Okay, right.
Not necessary.
All right, good. Yes, okay, great. Let's just plow on. Oh goodness, I've got more examples. Okay, so every train in Britain runs late. So we can translate that as follows. So we need a predicate that is a train, is in Britain, and runs late. We do it like this. Everything is such that if it's a train and it's in Britain, then it runs late. So every train in Britain runs late is a universal generalization that involves a conjunction of two claims, that this thing has this predicate and it has this predicate. If that condition is fulfilled, then it has this predicate. If it's a train in Britain, then it runs late. Yeah, please.
Could I ask you to do an example similar to that one? And maybe if it touches stuff that isn't involved, then just say no. But what about something like everything that runs late in Britain is a train? How is that differently laid out?
Sorry, everything that runs late in Britain.
Everything that runs late in Britain is a train.
Okay, so that would be, well, so one way to do that would just be to change the dictionary. This is a PDF, so I can't actually change it. But I mean, if you imagine, if PX is runs late, and yeah, so just switch around P and R here, right? So if then it would have this logical form, right? Everything is such that if it runs late and it's a train, then it's in Britain. Is that what you want? Sorry, everything is such that if it runs late and it's in Britain, then it's a train.
Right. Okay.
Right?
Okay. That's good. This actually eases some of my concerns. So, all right, good. I'm ready to go on.
Okay. Good. Good. So yeah, what you're doing there is saying something that's. So you're saying that that there's this set which is the intersection of the P's and Q's, and then set R is a subset of the intersection of P and Q. If that makes more sense, does that make more sense, or am I confusing
that
now?
Makes really, really good sense. Yeah.
Okay, good.
Yeah.
Yeah. So all you were doing was asking if those set theoretical relations were the other way around, how would you formalize it? And really, what I've done is said because actually it's the same structure. You just need to plug in the P's, Q's, and R's in different places, or alternatively just write them keep them all in the same place, but change the dictionary, and then you'd get the same thing. So hopefully that helps. Maybe I've confused some people, but if that's clear to you, then great.
Yeah, that really was great. Yeah. Okay,
nice. So, right. So then, next example: all mammals have warm blood and hair. I suppose there would be some ambiguity. We obviously mean sometimes warm in this sense, this predicate followed by another two. You might think it meant warm blood and warm hair. Obviously, we don't. In this example, it's obvious, but in some instances, there might be more than one way of formalizing this out. Like having experience of doing this and writing it for homework for students, and then having a stack of things to try and mark and go through in seminars or in exams or whatever. It's sometimes very, very easy to find examples where it's perfectly clear to you when you write down your sentence in English how you'd imagine the logical form coming out, and then you find that other people have a more intuitive way of reading a sentence that you didn't even imagine in the first place, and then when they write it down you go, oh, I see, okay, yeah, that's acceptable because you read it a different way or something. So there's a bit of an art to this, translating from English into first order logic. Sometimes there's more than one right way of doing it. Anyway, it becomes clearer the more you do. I think with this, it really does reward like what am I trying to say? It rewards you doing lots of different examples, and you get better at it if you do that. Anyway, so if we have this sentence, all mammals have warm blood and hair, then we have the dictionary PX being is a mammal, QX being has warm blood, and RX has hair, then everything is such that if it's a mammal, then it has warm blood and hair. So we're expressing a similar type of relation here, but we're saying there's this set PX, and the intersection of QX and RX is a subset of PX. So if that set theory stuff doesn't help yet, don't worry, because we'll be spelling it out with like pictures and stuff later on, so anyone will be able to understand what I'm saying. Okay, good. Okay, let me just have a sip of this drink, one sec.
When people start about incorporating pictures and shit, I feel so stupid all of a sudden. I feel like in kindergarten again. They're like, okay, teacher, bring out the pictures. It's okay, though. It's okay. I understand. You know, the scientific part behind it. It's visual. You see it, auditorial. With it, you know, you catch on faster. But I know if it's just the thought that came back that I'm back in kindergarten. You know. And,
yeah, well, I think people have different ways of like learning and understanding and stuff. And like, I'm a very visual like learner or thinker or something. So like, I always have pictures going on in my head for these things anyway. So
me too. Cool is that? Huh? Yeah, Minority Report. Ting. Yeah, I know that. Yeah, but it's a good thing. You know, it's perfect.
Yeah, good. All right, so all possums are in Australia. We would just have A as a constant for Australia. Again, it's a constant, doesn't need to pick out a person, can pick out things. P of X means X is a possum, and R of XY means X is in Y. So then we would say, look, everything is such that if it's a possum, then that thing is in A, Australia. So all possums are in Australia. Everything is such that if it's a possum, then it's in Australia. That's how we would translate that. Every mammal indigenous to Australia is marsupial. Again, A for Australia, PX for X is a mammal, QX for X is a marsupial, and R of XY for X is indigenous to Y, and then you'd write it out as everything is such that if it's a marsupial and if it's indigenous to Australia, then if it's a mammal and it's indigenous to Australia, then it's a marsupial. So the intersection of being marsupial and being indigenous to Australia is a subset of being a marsupial is a subset of the intersection of being a mammal that's indigenous to Australia. Good.
I'm sorry, I have a stupid question. Can you go back one slide, please? Shouldn't in the first example Y should be A, because you're using Y as a second ingredient in the second example? You said A is Australia, PX X is A is Australia, X is a possum, X is in Y. What is Y in the first example?
We up here in this one.
Yeah.
Yeah. So it's just a placeholder. Y is another variable.
If X is a possum, so X is a possum in Australia, but Australia is already A, so why use Y? That's what I'm.
Yeah. Okay. Good. So what I've done is I've got this constant here, and in the formula I've put it into the Y slot that was open in here. So two open slots.
I get it.
Yeah, no, it's a good question, because I filled the X slot with the quantifier by saying everything fills this X slot, or at least everything, if it fills this X slot, then it fills this X slot. But so this is the difference between a quantifier and a constant and a variable is picked out quite nicely here. So Australia is a specific thing, which is why I plugged in A for Y. I filled that hole in a sense. And X is the hole has been filled, but it hasn't been filled by a specific thing. It's been filled by everything.
Yeah,
in
exactly.
this
Because
set.
left as the placeholder example, and then used for the actual actual what's the word? Sum, notification,
Yeah,
notation,
yeah.
whatever.
This,
Then you're using the actual content. Yeah, okay, I got it. I got it.
yeah, that's right. So this, as you said, this is a placeholder in the dictionary, and then this is a formula, which
Oh yeah,
is
formula. Damn, it's
yeah.
blank. Formula.
And because there's and we'll go into this in more detail later on anyway, but just before we get there, so it's clear as we're
Yep.
on this.
Like you said with pictures, it's clear to me now. First, a dictionary. Like I said, it's a dictionary. It's a placeholder. Use your placeholders as indicators, and then when you do your formula, of course, you use the actual content. I get it. I get the
Yeah,
picture.
right. And so we can't give a truth value to this if there was a placeholder like y that didn't have a quantifier ranging over it, and it hadn't been filled by a constant. So if y was still in here instead of a, then it would mean that we wouldn't be able to attach a truth value. We wouldn't be able to decide whether or not it's true.
Because nothing fills its place.
Yeah, exactly. It hasn't been bound by a quantifier or filled with a constant. So like I said, we'll get onto that more as we go along. But you have so this variable is bound by the quantifier, and this one is filled by the constant, the place that would have a variable anyway. If the variable was there and it wasn't bound by the quantifier and it didn't have a constant filling it, then we'd say it was free. And at least the way that I'm presenting this, that you don't have, if there's a free variable, the formula doesn't have a truth value. There are other ways of doing predicate logic where you can get around that. So if you're picking up a textbook on predicate logic, some people will specify that there is a function that fills in all free variables in order to assign truth values, even if there's a free variable. I'm just going to say, well, I'm doing it a different way. I'm taking a slightly different tradition or whatever, where I'm saying if there's a free variable, then that doesn't count as a well-formed formula. So if you pick up Quine in his book, what's it called? Maybe it's just called Introduction to Logic, and I think his first order logic does it a different way, where you can have free variables, but you have a function that fills that in. Anyway, here, the way that I'm teaching it, without any of the digression into how other people would do it, is that, yes, this needs to be, both of these places need to be accounted for in one way or another. It has to be accounted for by a quantifier, or has to be accounted for by being substituted in for a constant. Anyway, yeah, so just as a little side post, if you pick up a book and they do it a different way, there are other ways that people do this.
Yeah, you're just given the secure way. It needs to be filled so you can make sure that the eventual conclusion comes out as it is, and you have other people that say you can play with it. But yeah, I get it. You're giving us the side wheel version, which is always sure of good to be used.
Yeah, I think, yes, that's right. I think this is easier to understand as well. It's more intuitive. Anyway, let's crack on. All right, so if we've got more than one quantifier, so here's one case, right? There's someone who loves Bob. We can do this. B is Bob. L is the two-place predicate for X loves Y. We can say there is someone some X who loves Bob in that way. And if you wanted to say Bob loves someone, so it's like the other way round, then we still got the same dictionary, but we just, instead of B being the second argument place, it takes the first one instead. So instead of there is an X such that X loves B, we say there is an X such that B loves X, right? But then if we want to say there's someone who loves someone, we don't need to have the constant involved anymore. We just need the dictionary to be that. We'll have two quantifiers. There is an X and there is a Y such that X loves Y. So it's not much to it. I mean, you can basically, we're just having a string. We could have a string of quantifiers in front of our formula, as long as each, it's quite nicely, I suppose, fits to what we were just talking about. But we'd need to have at least one quantifier for each variable that would have been unbound. Otherwise, we need to bind every variable that's not being filled with a constant. Yes. Okay, good. So hopefully that's fairly straightforward. Is that clear?
I think
Yes.
so far, yeah. Yeah, yeah.
Yes,
Yeah.
it is. It is.
Good, good.
Sounds logical.
And then this is exactly the same, just with universal quantifiers in place, and all I've done is change someone to everyone, right? So everyone loves Bob, Bob loves everyone, everyone loves everyone. So it's easy, we're just putting in universal quantifier instead of existential. So done it. The upside down A instead of the backwards E. But slightly more nuanced case, right? If we say everyone loves Bob, and Bob loves someone, obviously we know how to write both of those two. Then if we want to say the slightly more nuanced case, everyone loves someone, right? Say everyone, that for all x, there is a y such that x loves y. This is where it sort of gets easy to make mistakes. Let's see. Yeah, so just pay attention really to the difference in the bottom bit only. So in this previous example, everyone loves someone and someone loves everyone, right? It's not really that subtle a distinction, I guess, but these can be when we go on. But the order of the quantifiers makes the difference, right? So we're not changing around the order of x and y in, right? And as I'm sort of slipping between the two slides, it's only the order of the quantifiers that changes. For us saying everyone loves someone and someone loves everyone. Sorry, this way around, right? It's just there is an x such that he loves everyone, or there is something such that for all y, x loves y, meaning someone loves everyone and everyone loves someone for all x. But there is a y such that x loves y. Like all that's different is the order of the quantifiers between universal and existential. Whether the loves relation goes from everyone to someone or from someone to everyone. So it's obviously it's not really that complicated. I suppose it's a bit like if you just started plumbing or something and you've got like a connective for a pipe that goes from a big end to a small one, and then like the opposite type of connective that goes from a big pipe to a small pipe. Right? You need to know the difference between going from a small pipe to a big pipe and going from a big pipe to a small pipe. Right? This is the difference between these two bottom examples. You need to be able to get them right, or otherwise you can have water all over the place or whatever.
I had a similar mental image of that, but for me it was only from one person to everyone, from everyone to one person, because some of these things are assured. You know, there's everyone, it's everyone, it includes everyone, and someone, it could be someone, so it's going from an insecurity to security, something that is sure and something that could be sure. Yeah.
Yeah. Okay. And so the existential quantifier doesn't say. Although, on the one hand, I suppose it says that there is someone, it's got the word one in it. It sounds like there's one person. Existential quantifier, in a sense, means there's at least one person. It doesn't say it's exactly one. It's like saying it's not none, in a way. It's just, it doesn't apply to nobody, is how you can read the existential quantifier. It at least applies to one person. So yeah, it's got the kind of uncertainty about like how many people it is that it applies to. It's just certain that it doesn't not apply to everyone. Whereas a universal it is, I guess, in a sense, it's more certain. It kind of applies to everybody. Although we'll see later on that it's kind of interesting case comes with the universal where because otherwise it becomes messy, we will end up saying that if there aren't any people, like when we look at it later on, we'll be talking about the domain. If the domain is empty, then you can universally quantify into that domain, and it will be true. So if the domain is empty, then then, so for instance, say that there aren't any people that live on Mars. So if I say something like all Martians have a terrific sense of humor, then that would be true, but only because there aren't any Martians. Whereas if I said there is a Martian that has a terrific sense of humor, that would be false, because that actually it picks out and it's saying there is something which is a Martian. Whereas when you say everything, you don't automatically, it doesn't require that any actual thing exists. It's just saying that it's not false for everything. Anyway, well, this will become clearer as we go along again, but while that's slightly counterintuitive, it's needed to make everything work right. And it's actually one of the differences between Aristotelian logic and modern logic. And it sounds like a trivial difference in a way, but that for Aristotle, if you say everything has a terrific sense of humor, then you're committed to there being something that has a terrific sense of humor. Whereas in contemporary logic, you're not. So universal generalization doesn't carry with it existential weight in modern logic, whereas it did in Aristotelian logic. So there are, maybe at the end of this, I'll talk about the differences between syllogistic logic, Aristotelian logic, and the logic that we will have done by that point. And we'll see how we can situate Aristotelian logic as a kind of part of this modern logic. So what happened was Aristotle in like 350 BC comes up with this type of logic. He was like so much cleverer than everyone else around him that no one really did much to it for a long time. In the medieval period, people rediscover Aristotle because it had been, well, I say Western people in Europe rediscovered Aristotle because they'd forgotten about it. The Dark Ages or whatever had happened. And it was being widely read in the Arabic world, but it wasn't being read in the West. And when they rediscovered it, it ushered in a new golden age for logical development. But still, they were so indebted to Aristotle, they just referred to him as the philosopher, or whatever. So that there's this almost religious awe for how great Aristotle's achievements were. It ends up with Kant in like the 1700s saying that logic took not one step forwards nor one step back since the days of Aristotle. But something started to change in about 1850 to the end of the 19th century, where people questioned the doctrines of Aristotelian logic, and we get the logic that we've got now, which was invented by a bunch of mathematicians and philosophers and stuff. But part of what they did was relax certain Aristotelian like principles of logic. One of them was the behavior of quantifying universally and existentially, and using, I mean, Aristotle had symbols that were to stand in for, well, terms, a bit like what we've got for constants and predicates in a way, but he didn't have the distinction between constants and variables, which was something that helped out logic, and the idea of having a quantifier as a distinct part of the formalism. Roughly those three things are what makes modern logic distinct from Aristotelian logic. So a lot of the time you hear people talk about syllogisms. Strictly speaking, none of the logic we're doing will be syllogisms. You can express syllogisms, but they're just a much more restricted type of the logic that we're doing. What we're doing has much more expressive power. You can express syllogisms in it, and you can express things that Aristotle couldn't, because our logic is just better. So there was a distinct step up around the beginning of the 20th century, which is why, like computers could happen, was because we moved forwards in a way that we weren't able to do for like 2,500 years roughly before that. There was big changes. Anyway, I'm again getting sidetracked.
You know what comes to mind? You know who I think was an important factor? Mr. Boolean. and
The
if
pool, yeah,
or and
absolutely.
then, because when I first learned it with that stuff with my Commodore 64, and if or then, and I went like, oh, this makes sense, you know.
Yeah, right.
And when I see it, you know, it's I just dabble a little bit in logic and whatever, because I normally do medical stuff, you know, do sports care, a bit of psychology and all that stuff. So this to me is also interesting to see that it has such similarities to what I know before, that I think I'm going to catch on to this, you know, because it makes sense, it's logical. Why not? Aristotle did it, Plato,
Mhm.
Socrates did it over 2,000 years ago. We had 2,000 years to tinker with it, and of course it became an expression in the language, you know. And I just love to see the short development it already did from my childhood to now. Just compare how much it did actually from conception to now. You know,
Yeah,
yeah.
it's cool.
Anyway,
It is cool.
yeah.
I mean, I think it's cool. I guess you guys do as well, seeing as you were turning
Hey,
up.
you wouldn't be here, you know.
Yeah, that's right. All right, so let's do a bit more of it then. Whilst I've been sidetracked quite a lot, um, doing some more cases with more than one quantifier. So if we say every country has a capital city, then we have it as our dictionary. P, X means it's a country, and then C of X, Y is X is the capital of Y. So we would have that. Okay, so this is a nice example, right? We've got everything is such that if it's a country, then there is a Y such that Y is the capital of X. So here we've got our universal quantifier, and I'm saying this now, but I know it doesn't really matter. But anyway, look, the point is that within the scope of the universal quantifier, we find an embedded existential quantifier. So the range of the existential quantifier is only here. The range of the universal quantifier is over all of this stuff. So any instances of X following, we know that it ranges over the entire formula that comes after it, whereas the instances of Y only comes after it. Well, in a sense, it doesn't really matter, because if Y was inserted here in between the universal quantifier and the rest of the formula, it wouldn't really make any difference, because there's only one instance of Y in the whole formula anyway. So it wouldn't lead to an ambiguous statement, or wouldn't change the truth value. However, strictly speaking, this is the more precise way to write it, because if there was an instance of Y somewhere before this existential quantifier, then we would mess things up by sticking it in here. It would be now ranging over the whole thing. When we're saying every country has a capital city, strictly speaking, we want to write it like this. Sorry, were you going to say something there?
No, I was just going to say that makes sense.
Okay, good.
That's all. Yeah, I'm following.
So another example, if we wanted to say every calf has a mother. So hopefully, when we're saying every, we can start to think about the fact that it's going to have a universal quantifier in it, because we're talking about everything, blah blah blah. And when we have like a, in that sense, we know that that's going to be talking about particular things in a certain way, but not in such a way that we can name that thing. Otherwise, we could use a constant like a mother, a car, a blah blah blah. So hopefully, just by looking at this, you can already start to think, well, that's going to be a universal quantifier for this part of it. The fact that we're talking about a particular thing, or a thing, but without naming what that thing is. So we want to talk about it in a kind of oblique manner. So we're going to need an existential quantifier for that. We're going to need to have predicates for being a calf, and we're going to have this relation of being the mother of, because obviously calf and mother is some kind of relation that relates these two things together. So you can pull out of just looking at that sentence that it's got these various logical parts to it, some kind of quantification over everything, some kind of like existential quantification, some kind of predicates going on, and some kind of like relations going on. And we would write it like this. So everything is such that if it's a calf, then there is something such that it's the mother of the calf. So every calf has a mother. Everything is such that if it's a calf, then there is another thing, which is its mother. That's what that says. So there's lots of different ways of, like, you know, it means this with the dictionary, but if you just want to say for all x, if px, then there is a y such that mxy, sorry, myx. So that's what this sort of says, without having to. That's like just what the logical form of this says, without really knowing what it means. And then when we've got the dictionary, you could say it as just every calf has a mother, or you could say everything is such that if it's a calf, then there's a thing which is its mother. That would be another way of, like, using the dictionary to say what this says. So translating from English into predicate logic sometimes has various different ways you can do it. Sometimes translating from predicate logic, even with a dictionary, back into English, there's various different ways, all of which are correct, doesn't matter. Saying every calf has a mother is a kind of succinct way of doing it. You'll find sometimes there'll be, like, you know, a more poetic way of translating this into English using a dictionary, and more cumbersome way. Doesn't matter which one you do, as long as it gets across the same logical form, as long as what you end up with in English is equivalent, then that's right. That's the right answer. Okay, so if you want to say there is an ultimate cause, it's the sort of thing you might hear on the internet of people saying stuff like that in arguments. We would write out the logical form of that like this. So you'd say E of x is x is an event, so it's a predicate of being an event. C x of y, x causes y. So there is an ultimate cause means there is an x such that for all y, y is an event, and x causes y. I actually don't like that. I think I should have written that with a conditional instead of conjunction. I think I should say there is something such that for all y, if y is an event, then x is the cause of y. Now, the reason I don't like this conjunction, the reason I think that it's a typo by me to put that in there, is that this says, the way that it's written now says something like, there is an x such that for all y, so every y is an event, so everything is an event, and x is the cause of y. But there are things that are not events, like, you know, a tomato isn't an event, it's a thing, and it's not proper to class. It doesn't come under the extension of the predicate event. So I would actually, if I was marking myself on this, I would drop my own marks, because what I want to express is something more like the ones we've seen already, which is a conditional between if everything is such that if it's a cause, then if it's an event, then there's a cause for it, rather than everything is an event and has a cause. So yeah, you often, as a rule of thumb, if you're if what you've got is a universal generalization, you're going to want conditional. If what you want to express is an existential statement, then what you want to use is conjunction. And I guess here I've just been sloppy in writing it out, and I've thought, oh, it's an existential, so I'll put in it a conjunction. Where in actual fact, because the antecedent of this is what I've bound with my universal quantifier, I've ended up saying something far too strong. I've ended up saying everything is an event and it has an ultimate cause. And what I wanted to say was everything is such that if it's an event, then it has a cause. So the difference between the two types of statement that I'm talking about now is if it was conditionalized universally, then that applies to my tomato, whereas if it's a conjunction generalized universally, then it doesn't apply to my tomato. So what's the thing I'm trying to say? I'm trying to say Everything. What it should say is everything is such that if it's an event, then it has this one thing as its cause. And that works for my tomato because it's false that my tomato is an event. But it's still true that if it was an event, then it would have this ultimate cause, right? Whereas the way I've put it is everything with the conjunction, it says everything is such that it is an event and it has this cause. But it's false because it's not, both sides of this aren't true. And both sides need to be, if this was a tomato, say, for instance. And because we know that with a conjunction, both sides of it have to be true for the whole thing to be true. Because this first bit isn't true, then the whole thing is false. Whereas with a conditional, the only way that it's false is if the first bit's true and the second bit's false. If the first bit's false, then it's fine. So basically, if a conditional is universal, it applies to everything, even the things that the antecedent doesn't apply to. So this maybe I've gone into too much detail here again, but it'll crop up again and again. So this is the first time I've introduced it, which is quite nice because I've made a mistake and I'm correcting myself and explaining the difference. It's one of the most familiar mistakes that you'll make. And with a lot of the, if you go through like the homeworks and stuff, have you still been doing that, Helena? I haven't been keeping up. Have you been going through
the quizzes?
Yeah.
Yes, I have myself, but I haven't recorded anything yet because I'm dealing with trying to learn editing a little bit.
Okay, right, fair enough. Well, I'm quite happy to put the exercises, a link to them on the videos or something if you want, so that people can have access to them to go through the homeworks, because I think that's the best way to learn this stuff.
Okay, yeah. So after this hangout, let's get together so that I can know what's okay to put and where to put it.
Yes, okay,
because people have been asking, and I've just been, well, we'll talk about it when we're done here.
Yeah, but we'll make it so that there's stuff that you can go away and practice and answers for them so that you know what you should have said. And yeah, one of the commonest mistakes is to mix up a claim with a universal quantifier and put a conjunction instead, which is what I've done here. Anyway, stop belaboring this point.
Right, so the main point here is that if you're dealing with a universal, try to make it work with conditionals, or
yes.
must you? And whereas
no,
with existentials goes with conjunctions, you don't have to.
You don't have to, but what you'll find is it's very unlikely that what you'll be trying to say will be a universal generalization with a conjunction. It's just so strong. It actually says that every single thing has a property or whatever, whereas if you're conditionalizing, most of the time you're going to say that everything is such that if it's a marsupial, then it's a mammal, right? Everything is such as if it's a marsupial, then it's a mammal. My tomato is such that if it's a marsupial, then it's a mammal, right? It's true of everything, including the things that aren't marsupials, because it's just making a condition. All marsupials are mammals, right? But so if you tried to add a conjunction in there, you say everything is such that it's a marsupial and it's a mammal. Well, now that stops being true of everything, right? That's just adding a conjunction instead of a conditional. Just doesn't express anything that you'd ever want to say. It's not like you can't say it, but try and think of an example where you're saying two predicates that actually apply to every single thing. You're just never going to say. It's far too strong, unless you're really ambitious, of course. But and then with the existential claim, so let's see, how does that work? So you've got that's normally you'd say something like so if you go, oh, this is a red car, what you want to say is there's this thing, it's red and it's a car. Well, you don't want to say there's this thing that if it's red, then it's a car. I mean, that's like, now you're making the opposite mistake. Instead of saying something too strong, you're saying something too weak. There's one thing, at least one thing, such that if it's red, then it's a car. That's not what you mean when you're saying there's a red car. You're not saying there's this thing which could be a red car if only it was red or something. What you're saying, there is this thing, it's red and it's a car, it's a red car. Right? So often what you're doing with an existential is you need that appropriate level of strength. And with the universal, you don't want to say something too strong because the range of your quantification is already quite high. So you need to sort of balance these two things together. You don't have to. You're not making a logical mistake otherwise. It's just that you're saying something that you're very unlikely to want to say if you make that mistake. So when translating from English into first order logic, it's not going to often be the right answer if you mix those two things up. It's a pragmatic thing. It's not strictly speaking a logical error. It's just that, in this case, I ended up saying something way stronger than I wanted to by putting a conjunction instead of a conditional, because basically it was a universal claim. At least this bit was universally quantified over, and by conjoining it with something else, I made a claim that was far too strong. Anyway, let's crack on, because time is passing as always, and there's still quite a fair bit on this lecture to go through. So let's whiz through these bits. So we've got now all of the bits of vocabulary that make up the resources of the predicate logic, predicate calculus. So just to recap, here are the bits. It starts off, it's also got the propositional letters, so we can still have propositional letters popping up in formula. I haven't used them in any of these examples, but say this, for instance, that could have simply been the lowercase p, just as we had in propositional logic. It could have just been like, everything is such that if p is true, then there is a y such that myx or something, right? It's atomic propositions that we've had from propositional logic are still part of the vocabulary. I just haven't included them in any of the examples because I've been trying to show you the new stuff. But this is still part of what we've got. It's still all part of the same logic. So we've still got propositional letters. We've still got the propositional connectives. I mean, obviously, I've shown you ones that have propositional connectives, so that should have reminded you that we're one big happy family. We've still got punctuation. Obviously, we've still got brackets, and I've been introducing to you the constants, predicates, relations, basically the same things, predicates. And now we've also got quantifiers as well, and variables. So just for the sake of knowing which way around they go, constants are going to start from the beginning of the alphabet. Variables are going to start mainly at x, y, and z. And if I need more, I'll probably subscript these with like x1, x2, x3 or something. Beginning of the alphabet are always going to be constants. Around the end of the alphabet are always going to be variables. So that's how you know which is which. It becomes second nature, but I suppose to begin with, it's not immediately obvious. But yeah, if you just keep that in mind. And then that's it. That's all that we've got. So this is a propositional calculus, and then predicate calculus includes all of the propositional stuff, but it also has other stuff. So the language that we're speaking is greater, but like I said before, we're just adding houses to our street rather than starting a new one. And in terms of the grammar, it's the same sort of thing. We've got our 3 grammatical rules from propositional logic. So any proposition letter on its own is a well-formed formula. If A is a well-formed formula, then checking the negation on it is as well. A and B are 2 well-formed formulas, then you can binary bind them together in any of these ways. But also we've got if P is a predicate and A is a constant, then that counts as a well-formed formula, P of A. If R is a relation of n places and A1 to AN are constants, then R of A1 to AN is a well-formed formula. So if R is a 2-place predicate and you have A and B, then R of AB would be a well-formed formula. Just writing it here with n places just to remind you that there's no limit really on how many places we can have in a relation. And then here, this is the last bit really of the lecture, is just to very quickly introduce to you the idea of substitution. So if we have a formula, and remember this, uppercase A means that it's, in a sense, it's a type of variable. I'm just using it as a way of saying it's a formula that could be of, so A here, and indeed in this entire slide, this capital letter A could be like, it could be this, right? A could stand for this, right? It could be anything of any arbitrary complexity. It's just a formula as long as it's well formed and it fits with the rules of grammar, whatever. It's just any well formed formula. It could be this complicated. It could just simply be this complicated. It could just be the proposition letter P. Doesn't matter, right? As long as anything really, as long as it's a well formed formula. So it says, so universal quantification with a formula A, and then this square brackets x dash A just means so for any formula any constant, then sticking a universal quantifier in front of it with this substitution schema thing at the end, it's just by replacing a where it features, so replacing every instance of lowercase a in this formula by a variable x. So it's like what would happen if you had a formula that said of various individual specific things, or at least if a formula that named A maybe stands for Alex or something. What we're doing is if you universally generalize out of that and say, instead of saying things about Alex, you're saying for all x's, and then every time A or the word Alex appeared, we substituted that out and put x in instead, then the result would be a well-formed formula. And the same for, it's just exactly the same rule for existential. If you hit a formula and you do an existential in front of it and this substitution schema on the end, then what it means is every time A appears, every time lowercase a constant appears in this formula, uppercase A, then we're replacing it for x. And then that's an existential generalization from it. So, for instance, if the formula was for the sentence like Alex is a philosopher or something, then the result of this would just be to say something is a philosopher, right? And if the formula here said Alex is a philosopher, then what we're doing here is universally generalizing and saying everything is a philosopher. I mean, obviously it wouldn't be necessarily true, but the point would be, if you've got a well-formed formula that has a constant in it, you could make a universal generalization out of it. So if it's true, if it's a well-formed formula, Alex is a philosopher, regardless of whether it's true or not, it's a well-formed formula, then you can make another well-formed formula by going, everything is a philosopher. And again, if it's a formula that Alex is a philosopher, then it's a formula that there is something which is a philosopher. Right? So that's kind of a technical rule, but if as long as you've got that in your head, then you've got the resources to say anything in predicate calculus or first order logic. Okay, so I had an example under here, which maybe I should have been referring to. But look, if A is this formula, that P of A, Q of A, and F of B, then A with the substitution schema gives you P of X, Q of X, and F of B. So I've taken it out each instance of A, and I've substituted in X's instead. But I didn't take out the instance of B and put X's in because it was X of A in the substitution schema. So every time you see A, put X in the place. And then I'd have to have a quantifier in front of it as well, just to make it a well-formed formula. But yeah, hopefully that makes sense. Have we got any questions about that? Maybe that was too complicated at the end, but hopefully not.
That did make sense to me.
Okay, good. It will come in handy later when we start showing how to prove things in predicate logic. But for now, yeah, I think that's it for this week. I'm certainly not going to plow on to the next one because.
No, I think it's good to stop here.
Yes, definitely. It's dinner time for me as well.
Okay, so I'm going to go ahead and close off. And does anyone have any final questions about the actual material? If not, then I'm going to go ahead and stop the broadcast before Alex has to go eat, so that he and I can figure out how to get this material out, so that anyone who wants to can have it and practice with it.
Yeah, that's the only thing for me. That's what I need. I just need the reference material, the whole logic, the reasoning, the contextual. That's absolutely clear for me. But the only thing is, like I said at the beginning, the notation stuff I just have to get used to.
Yeah, right. You need to know the notation stuff before you can practice.
It's the lingo. For example, if you confront me contextually with stuff like this, yeah, I will have no problem doing A is equal to B or whatever and stuff. But I'll do it in a verbal way. This is just actual math notation. Just if I get used to this, then I'll just be up and along with the next.
Think how powerful we're going to be.
Yeah.
All right. So thank you so much, everyone, and I will be sending out a G+ notification about how you can access this stuff pretty soon.
Cool.